let's see, there's D71, D74, D75, and there are 2 papers in that volume, and there's a short review in the Confinement 7 meeting.
So I guess this is all on the archive.
And it's all on the archive, and then there's going to be +1 because I've got a paper that's almost finished that I'll come out with in the next, I hope this week sometime. And so maybe since this is a small group of people, I can be a little more personal in saying that one of the duties we all have as scientists is to be scholars. And so an interesting thing happens, which is often because of our own lack of scholarship. My lack of scholarship certainly is a problem for me sometimes. We miss certain things. So for example, it's very well known to people that now we can do strong coupling expansions using ADS-CFT. And in fact, ADS-CFT, well, for N = Fourier-Mills is a really important innovation. But there have been these ideas of trying to do ADS-QCD, which is a kind of strong coupling model. And very often I'll go to talks on this subject, and people will talk about it, and I'll say, well, and they'll compare it to Monte Carlo lattice simulations. And so I'll say, well, what about strong coupling calculations? And they'll say, well, that's what I'm doing, strong coupling calculation. I'll say, no, I mean old-time strong coupling calculations from the 70s. They'll say, what are you talking about? And so I think this is a case where it's good to know what the real issues are when we want to try to get to a quantum field theory without a regulator, because since Ken Wilson's paper in '74, we've actually known how to do strong coupling expansions. So the important thing I think about, it's really important to understand that these strong coupling expansions that we did before were abandoned in the end because there were some difficulties with trying to get to the continuum limit. So this was sort of an industry. There are strong coupling calculations you could do on the lattice in the Euclidean space. There were strong coupling calculations you could do on the lattice in a Hamiltonian formalism of Kogan and Susskind. But they were abandoned because in the end we realized they were a model. And to get to the real continuum limit of the theory, you want to do better. And now maybe maybe using ADS QCD, you can get to the continuum limit, but that's the challenge. That's the hard part. And I know in ADS QCD, the problem is that you're dealing with small curvature and you want to get to very large curvatures, and that's the obstacle. In the old-time strong coupling calculations, the problems that we had were that we just simply couldn't make the expansions converge. And in fact, there were even some indications that there were phase transitions that we might encounter. So I think the right way to think about a lot of these strong coupling expansions is that they provide you with a model of QCD. And the model is probably pretty good in some ways, and then you also want to see how good where it falls flat on its face in other respects. And so for N = Fourier-Mills, that's another story. I mean, there you can pretty much do everything. But if you really want to talk about hadrons, this is an issue. And so what I want to talk about is something that's different, because it's not a strong coupling calculation. And in fact, this, as far as I know, is the only model in more than 1+1 dimensions. So this is in 2+1, which is really weak coupling. And what I want to stress, though, is that this is a model where, in principle, you can get to the critical point, that is the continuum limit of 2+1 dimensional gauge theory. But there is still something to be desired with what I'm going to show you as well. But what I really want to advertise, and where it really is different from other ways of looking at these problems, is that it really does not involve large coupling constant. It's really something that works at small coupling constant. So let me draw you a picture. Yes. It's a weak coupling expansion, but it's not the usual Feynman diagram expansion. So let's suppose we write down the Yang-Mills Lagrangian, so everybody knows what that is. So it's 1 over 2e squared. So we have f01 squared plus 1 over 2e squared, f02 squared plus, and then we should say minus 1 over 2e squared, f12 squared. And if you're in 2+1 dimensions, then it turns out that e squared goes like centimeters to the minus 1. So if we put in something with dimensions, which is eventually going to be our ultraviolet cutoff, we can write this as a over 2g0 squared f01 squared plus a over 2g0 squared f02 squared minus 1 over minus a over 2g0 squared f12 squared. And so here's where the expansion is. We make this g0 prime. And now what we say is that g0 is much, much less than 1. But g0 prime turns out to be less than, I don't know how much less than, 1 over g0 e to the minus 4 pi over g0 squared n. We're breaking Lorentz invariance. So this model is anisotropic. It has 1+1 dimensional Lorentz invariance, not 2+1 dimensional Lorentz invariance. And at the end of my talk, I hope I'll have enough time to say a little bit about how we can actually try to extend this to the Lorentz invariant theory. So I have a conjecture as to how to do that. And the conjecture might be wrong. But I feel that if this stuff is to go any further than it's already gone, that's the way to go about it. So when I say now that what's the advantage of doing this? Well, the idea is the following, and it's something, again, I'm going to go back to physics from the 70s. If you look at the lattice Hamiltonian theory, and you look at the Hamiltonian formulation, and you see then that electric fields are defined on the links of the lattice, and the gauge fields are also defined on the links of the lattice. If you simply say, I'm going to drop the electric fields on the links in, say, the one direction or the two direction, what happens is that the theory just breaks apart into a bunch of principal chiral nonlinear sigma models, which are completely integrable. And it all just follows from that observation. So that's where the motivation all comes from. And to do it carefully, you have to put it all in axial gauge, and I'll show you essentially how you can do that. But to draw a picture of the coupling constant diagram here, so here's g0 squared, here's g0 prime squared. Where we would usually study the theory in perturbation theory is we look around here. This is the continuum limit, or no cutoff. And this is the usual Lorentz invariant isotropic theory. So this is isotropy here. And where people can solve the theory is either, well, actually in 2+1, you can't even really solve it here because you have infrared divergences you have to deal with. But out here is strong coupling. And I should say that you can do, well, in 2+1, I guess there are ways of doing strong coupling in the continuum now. There are lattice ways of doing strong coupling calculations. I might add that there's a nice formalism of Dimitri Karabali and Parameswara and Nair. What they do is actually, in a certain sense, I think what's really nice about what they've done is they've essentially found a very nice parameterization of orbit space, and which is sort of another interest of mine. And using that, they can do strong coupling expansions. And I think that what's really wonderful about what they've done is the parameterization. However, their results can all be obtained by doing lattice strong coupling expansions. And on this line, the theory is integrable. So as what I was saying was that if you cut out some of these links, if you set g0 prime to 0, if you've regularized this theory, you have an integrable theory left over. And where I'll really solve it is here. And the reason for that, the unfortunate thing about this is if you look at this condition, you see that g0 prime is bounded by something which is not analytic in g0. And for that reason, we can't compare with perturbation theory. Because to compare with perturbation theory, we'd have to have some non-zero slope on this graph. So that's the weakness of this approach. But we want to study that shaded region. And what I want to show you is that, or at least argue, is that in this region, in the shaded region, we have confinement of quarks, we have a mass gap, we don't have confinement of adjoint sources. So it looks very much like the phase that we would like to see in a real confinement theory. It's not a super renormalizable theory because the principal chiral model is actually asymptotically free. So in some sense, what we're trying to do is perturb around the principal chiral nonlinear sigma model.
So when you talk about the principal chiral model, do you mean that model in 1+1 dimension?
Yes, that model in 1+1 dimension.
Dimensional reduction.
It's a kind of dimensional reduction.
Right.
Right. So let's ask for a second how we're going to approach this. What happens when we, and I don't know if I want to describe, unless people really want to know in detail, how you make the reduction, but let me say essentially what's going on, which is if you split space into layers, and these all have some thickness A. So A is the A that I'm talking about over here. Okay. Then there's there's a regularized form of the Hamiltonian. Normally you'd write the Hamiltonian this way, as H is equal to G naught squared prime squared over 2A, and then we'd have E1 squared plus G naught squared over 2A E2 squared plus 1 over 2 G naught squared A times B squared. So B is just F12. And in a strong coupling expansion, we would neglect this term. So if you have a regularized theory in a strong coupling expansion, you would just drop this term in the Hamiltonian. But we're doing something different, which is we're dropping that term. Now, if you go to an axial gauge, it's not compactification. It's I'll explain. It's a different kind of dimensional reduction, but it's not a compactification. Okay. So if we take an axial gauge, we take A1 equal to 0, then E1 is not equal to just minus I times the functional derivative with respect to A1 anymore. So if you can fix an axial gauge carefully, what you see is, in fact, that the right choice for E1 is it's an integral from minus infinity up to x of dx prime of d2 E2, where that's a covariant adjoint derivative. So what I'm doing, you can do this. To do it really carefully, you need to choose the right boundary conditions. So by infinity here, you would really specify exactly how you're doing this. This can all be done. The nicest way to do it is to choose cylindrical boundary conditions, which are open in the one direction and closed in the two direction. And then you see that there's a further constraint. This is obtained, by the way, just by solving Gauss's law. So Gauss's law says that d1 E1 plus d2 E2. Well, on the physical states, this would be equal to whatever charges you've got. So you might have to add some charges in here. Okay. So let me show you, if you do this thing, now I want to show you a different formalism for a slightly different approach, which is, doesn't this lift yet? I just let my eraser get away from me. So if you do this carefully, you can write down what the Hamiltonian actually is. We write A2, we replace it with a variable I'll call u. And u is equal to e to the I times the integral from some x2 to x2 plus a of A2. So that's within one layer. So you see I split space up into layers here. So this is now, so this is our discretization. This is actually like a lattice gauge field, but we're only writing it as a lattice gauge field in one direction. And we'll define some currents. So there's J mu left B, which is the trace of I times TB of d mu u dagger, where mu is 0 or 1, so it's time or the one direction. Let's see, did I get that one right? Yeah. And the right current is similar, it just has the u dagger and the d mu u reversed. And when we quantize now, these currents get promoted to operators. They satisfy a pretty standard current algebra. And so now we'll write down the Hamiltonian of the non-abelian gauge theory. So H is equal to the sum on x2. So the x2s are discrete. So I should have said that's the two direction. So let me just quickly show it for you here. That's 1. That's 2. And this is the integral dx1 j naught right b squared plus j1 right b squared. And by the way, the right could be replaced with left. It doesn't matter. If you square the left current or the right current, it doesn't matter. So that's the first term we have. And that term has a 1 over 2 g naught squared in front of it. So I'll call this h naught. And then there's h1. H is equal to h naught plus h1. And this is the term that's really given, it's just essentially the integral over E1 squared. So actually, good, I think I've done everything right. So this thing would have a g naught prime squared in it, and it's obtained by solving Gauss's law. And what it actually is, it's minus the sum on x2, g naught prime squared over g naught, I think it's the fourth, times a. And, no, I'm sorry, it's g naught squared. We have to integrate over dx1 and some dy1. We have x1 minus y1. And now we have some stuff that involves the currents. J naught left, x1, x2, b minus j naught. Well, I'm running out of space, so let's move it down a bit. So this is a really horribly looking non-local sort of object. And you would, and in fact, it sort of took a long time for me to even take this thing too seriously. By the way, if you want to put in source terms, you would simply add a minus, a charge located at x2 here. So you can accommodate sources. The reason why I sort of never took it that seriously before was because it looks so non-local. But there's a motivation for studying such things. Again, I was talking about scholarship. We all, I think, if we're interested in the confinement problem, have read a Tufts papers pretty well, and we know Tufts' motivation for thinking about magnetic monopoles in QCD. But few of us have thought hard about Mandelstam's motivation for it, which was actually quite different. What Stanley Mandelstam did was he looked at axial gauges. And he argued that it was very hard to make a vacuum which would have a thermodynamic limit if you simply looked at the perturbative vacuum because of the non-local character of this term. And so he said that you had to have something that was rotating this vacuum locally in order to make something that would have a finite vacuum energy density, which would have a good thermodynamic limit. And he argued that those things that could make these local rotations were magnetic monopole creation operators. But instead of, so that in fact was really what kind of interested me in this whole thing.
So can I just check
Yeah.
I'm understanding the algebra indices correctly there? So in that,
Yeah.
in H naught, we're just summing over, in H naught, we're just
Yeah.
summing over the B's.
Yes, right, we're just summing over B's. Right, so
H1, what's?
So H1 we're summing over a lot, okay? So we have to sum over X2 in both of these things. So what this does is it couples the layers. So here you have J0 left in this layer, and now below it you have J0 right. So this takes the color charge, really that's the right way to think of it, in one layer, and you subtract the color charge in the layer below it. And then if there's any source, the sources live in the layers in between. So if there's any quarks, they live there. And you actually look at the quarks in the whole layer when you look at this expression. So in fact, there should be an x1 here, and there should be a y1 here. And now what you do is you look at this difference between the color charges at one value of x1, and now you take y1, and you integrate x1 and y1, and then it gets even worse because instead of multiplying it by something that dies off with the power of x minus y1, it actually grows. So to do this, to derive this, as I said, you have to be very careful about boundary conditions. Whenever you've got anything non-local, you can worry about whether your thermodynamic limit's going to make sense. So in the original derivations of this is actually starts from the Kogut-Susskind lattice formulation, where you see that the Kogut-Susskind electric field operators are nothing but these current operators. And if you then carefully do the axial gauge fixing there, you see that if you take the continuum limit in the one direction, you just get this Hamiltonian. So that's done in the first of those papers up there. Yeah, it couples stronger. The farther it is apart, it's highly non-local. That's right. But now if you think about it, why is that? Well, it's because this is Gauss's law we're solving. So Gauss's law tells you that the flux in the one direction is determined by everything that flows in the two direction. So if you have more flux in the two direction, you're going to accumulate more and more flux in the one direction as you move along. So that's why it looks so horrible. But it comes from a local theory, so you might think if you really try to analyze it, maybe it's not going to end up being so horrible. And the surprise, I think, is that in the end, it's not as bad as it looks. At least in my humble opinion, it's not as bad as it looks. This is not the whole story, because we have to supplement this thing with the Gauss's law. And so remember, we solved Gauss's law to get this thing, but we didn't solve all of Gauss's law. There's one constraint left over that we have to deal with from our boundary conditions. I suspect Stanley Mandelstam took the same boundary conditions, although I don't know, because he wrote down the same constraint in his discussion. And it's that if you take this thing, J0 left x1, x2 minus J0 right x1, x2 minus a minus the charge, and integrate that over x1, that on physical states has to be 0. And this has an SU2 algebra. So in fact, this depends on x2, this operator. So that's what Gauss's law is reduced to. Now we have Gauss's law that acts between the layers. So someone asked me earlier, is this compactification? The answer is no, it's not compactification, but it is a reduction. Suppose we take G0 prime to 0, then this term goes away. And now what you simply have are a bunch of these things. So the layers break apart. So all of these principal chiral sigma models are just simply ignoring each other, except for the constraint. The constraint is actually making them respond to one another. So it isn't quite a 1+1 dimensional theory. And this fact is responsible for understanding confinement at a very basic level in all of this. So let me tell you right now, we now know enough actually to see that there's confinement in this theory. So I'll call it vertical confinement, and you'll see why. Let's suppose we put a quark here, and an antiquark here, and ask, what is an eigenstate? With those sources placed in theory. This theory has a gap. It has a mass spectrum m sub k, which is equal to the mass gap times sine of pi k over n divided by sine of pi over n. Which was, I guess it actually sort of comes from the Gros-Neveu model, but the principal chiral sigma model S matrix is like a product of two Gros-Neveu model S matrices. And so you can find this mass spectrum. And so what happens is that if you take a state which is the ground state here, and the ground state here, and so on. So we have ground state everywhere we can. We try to make the ground state compatible with these two sources. Then this condition implies, because this couples one layer to the other, that this state is not a color singlet. So in these layers between the quark and the antiquark, you can't have a color singlet.
You're saying that can't annihilate the vacuum or something like that?
Yes, that has to annihilate the vacuum. And if there's no charge in between, then both states can, these two states can transform the same way under a color rotation.
Chiral model vacuum, both of those currents annihilate the vacuum. Is
Yes,
that
right.
Yeah.
But now the problem is we put in a charge. So this state can't be a color singlet, but the Merman-Wagner theorem in 1+1 dimensions tells us that if we have a non-vanishing singlet vacuum expectation value and it's orthogonal to the ground state, which it has to be because this is an eigenstate, then it must not be vacuum. So I shouldn't say orthogonal to the vacuum. If it's an eigenstate which is not a color singlet, it cannot be the vacuum. And since the theory has a gap, that means it has to have an energy of at least m1. So now what we have is a potential which is equal to m1 divided by A times the separation. So that immediately gives us confinement in the vertical direction.
So why does the vacuum energy on each layer in between the two quarks have to be non-zero?
Because it can't be a color singlet. So in other words, let's just look at this layer. Okay? So here there's a quark, so this Q isn't zero. So now if you consider this, the difference between these two things, you don't get zero. Well, that can't happen if one side is a color singlet and the other one isn't. Okay?
So the lower bound you're thinking of is just sort of the excitation of one particle in
Right.
some sense in
Right.
each layer.
It has to be at least that. So maybe I should have written it this way.
Yeah, that's the
So what you're saying is just that you have some kind of color flux tube between the two quarks and the...
There is a color flux tube. And in
is
fact,
M1.
and if I have time, I'll actually the last calculation I've done in the next paper that I'm trying to get out is actually trying to understand in detail this color flux tube. It's built out of the soliton-like excitations of the principal chiral model.
Is that really, is its tension, you would think maybe it's much larger than that, the tension?
Yeah, but
It's hard to visualize how one particle state...
Well, I've actually calculated,
here,
I
right?
calculated the potential in this perturbation theory I'm talking about. So in fact, it's not much larger. Now, but let me tell you though, in the ordinary theory, in ordinary supernormalizable Yang-Mills 2+1, it's quite different from this. So this theory is really very different because of the fact that it's in that shaded region. It's not coming from the isotropic line. There's a crossover.
What happens if you put representation that has n boxes?
Okay, in this direction, in the vertical direction, it just comes from this formula. It has a sine law. Okay? But let me answer the question about the other direction for a second. Okay? Suppose you put a quark here. And an antiquark there. What happens then? Well, if G naught prime is strictly 0, electric flux is completely unconstrained in the horizontal direction. There is no potential. You can just make electric flux in the horizontal direction at no energy cost. Okay? So, but what happens, of course, is suppose now we make G naught prime small. And in fact, this was, in the first paper, this was sort of a flaw because I didn't know how to do perturbation theory in G naught prime at that time. Well, you would say, okay, suppose now I try to take some electric flux from here and I move it into this layer here, and then I try to move it back before joining to here. Then what happens again is that you must excite this vacuum, and in fact you should excite a pair of soliton-like particles, Fideo's analogic of particles there. So what will happen is the presence of the gap in the adjoining layers will give an energy cost if electric flux is allowed to move in directions other than straight lines. And so what you have then in this direction is a horizontal confinement. By the way, I want to say this needs to be considerably improved upon, and I'll tell you how you can improve it. And what you find then is that the string tension is just a 1 + 1 dimensional string tension, and it's just the Casimir times G naught prime squared over A squared. So to continue the answer to your question, if you look at higher quark representations, here you get a sine law, here you get a Casimir law. So it's really not a rotation invariant theory at all. Okay, but maybe you had something else that I'm overlooking. I don't know if you wanted to. Does that?
I was wondering whether anality has to do anything with this vertical confinement.
Yeah. Well, you still have confinement with higher quark representations with the string tensions, I say, obeying different laws in different directions. If you put adjoint sources into this system, you don't have confinement.
Vertically?
Either way. So an adjoint source actually has finite energy. That's because you can pop some of these particles out of the vacuum. So there's an energy cost, but it's a finite energy cost. So there's no gluon confinement, if you want.
So the basic particles of the principal chiral model actually not color singlets.
Right.
Gauge theory point of view.
Right.
Those are sort of horizontal gluons, if you like.
It's a little bit like Charles Thorne's old model of sort of having strings of gluons built out of gluons, except the gluons are only vertical electric flux. The horizontal electric flux is just simple 1 + 1 dimensional horizontal electric flux. Vertical electric flux is built of these massive particles which have the same colors as gluons. By the way, this tells you why you have to have this relationship. It's because this thing goes like the gap. And in order to make this work, you need the string tension in the horizontal direction to be the potential in the horizontal direction to be much smaller than in the vertical direction. And that's where this condition comes from. Yeah.
This mass spectrum is reminds of the Chebyshev polynomial.
I'm sorry, say it again?
This mass spectrum
Yeah.
for a single layer looks like a Chebyshev polynomial.
What kind of polynomial?
Chebyshev.
Chebyshev. Oh, I don't know.
But which implies some SU2 underlying structure.
It's possible. I don't know. Yeah, I mean, it's the way. Yeah, I don't know. I mean, my understanding of it isn't that deep. I mean, there's some papers of the Berlin people in the 70s where they worked out the mass spectrum of the Gross-Neveu model, and then Paul Wiegmann showed that essentially it's the S matrix of the principal chiral model is the square of the Gross-Neveu model S matrix, then with a projection built in. It's just mimics the Gross-Neveu mass spectrum. But I mean, I'm just sort of, I'm a very nuts and bolts kind of guy. There probably is some deeper reason behind it that I don't know about. So if you can actually do some more. Now, what happens if you actually try to turn on G0 prime? So can you say more than what I've said? And the answer is you can, because you know two things. One is you know the exact S matrix of the principal chiral model. But you even know more than that. You know some exact matrix elements of currents of the principal chiral model. And this allows you to find the low-lying mass spectrum.
Are you talking about G0 prime at G0 prime equals 0, or?
G0 prime much, much less than 1 over G0 e to the minus 4 pi over G0 squared n.
So are you meaning kind of a first order perturbation
Yes.
of G0 prime?
Yes.
That's the,
Yeah. And this allows you to find corrections to the string tension. And I should add for SU2 only. And the reason why it's for SU2 only is for a technical reason, which is we don't know these matrix elements for the principal chiral models yet. We actually do know them now for the Gros Niveau models for higher n, but it hasn't yet been worked out for the principal chiral model. It's tough because it's easiest when the excitations are sort of simple and they don't come in a lot of different varieties like they do when you take n greater than 2. So this is... so what I could do is just tell you what those corrections are and how they work. Maybe I don't know if I should write down the formulas in detail, but I'll just tell you the mass spectrum. So this may not look very beautiful if you really want to solve the rotation invariant theory, but let's scale our ambitions back a bit. I mean, we have a model. Let's see what it tells us. Basically, naively, you would just say the mass spectrum in our layers would just be 2 excitations of the principal chiral model. So these are what I tend to call FZ particles, Fedayev-Zamolodchikov particles, which is really an abusive language because people talk about the Fedayev-Zamolodchikov algebra, not the Fedayev-Zamolodchikov particles. But anyway, for me, it's easier just to recall these things that. And you can have 2 of them bound together in this way. Now, there's a linear potential between them.
so sorry, we're still working with a Q and a Q bar source, or now you're talking?
No quarks. So
This is the pure kind
pure
of
glue.
global set.
Yes.
But the particles of the principal chiral model aren't confined, right?
Well, yes, they actually are. They're confined in the point is if you had a static source, they're not confined. Let's ask what the excitations are. So for SU2, in a sense, they are confined because your excitations are of this form. So they are confined in that sense. For SU2, you'll find ring-like states. For SUN, you can have more complicated configurations. So the point is
I'm missing something. What's to stop you just exciting particles in a single layer? Is it to do with this constraint here? Or?
Yes, you can't do it. If you excite particles in a single layer, you must produce, in other words, even if the G0 prime was actually 0,
yes, right.
you have to construct only states that are consistent with that residual constraint.
And that's saying that you have to somehow clump them together into something that looks like a color singlet.
Yeah, you could make this very, very broad in this direction as G0 prime goes to 0. So in the limit that G0 prime actually vanishes, the potential between these things vanishes, but you still can't construct states which are not of this form by virtue of the constraint. So, in fact, this is physically really what the constraint is telling you. It's not giving you a potential, but it's telling you what kind of states you can make. So, the low-lying mass spectrum will consist of things like this. Now, where things get interesting is where these two particles overlap. So these are not free particles. They behave like solitons, but they scatter also like solitons. So there's a phase shift when they pass through each other. So that gives you a correction to the mass spectrum. Now, normally, if you took G naught prime very, very small, but not 0, and ask what that term does, is it just produces a linear potential between these two particles. However, when the particles are very close together and the potential is essentially negligible, there's a phase shift as they pass through each other. And this affects you get a modified WKB condition. And so there's a formula for the low-lying states, which is sort of a mess. If anybody wants to see it, I'll show it to you.
So what approximation are you applying in each layer of problem? The S matrix just tells you about asymptotic states and the phase they get from
Okay.
scattering, right?
So here's the approximation. We treat these particles, we treat the potential as being extremely weak, and we're looking at the lowest energy states. So we're assuming in some sense that the mass of the particles is very large, and they have low momenta. And so the point is when they're close together, we're ignoring the potential. And then we're asking, what would the S matrix then tell us? So you can write down a nice form of the S matrix according to the way the Berlin people do it, and you see, in fact, if you project these guys onto the color singlet sector, that it's just a phase shift. So we have a potential, of course, but still, when the particles are close together, we can think of it as a scattering problem. So that phase shift just gives us a boundary condition where the particles are overlapping.
So, I mean, I'm just trying to see how this phase shift relates to the spectrum. You've got some kind of equation where you use that phase, you have some boundary conditions, and then this phase shift enters in the same way that, when you write down a Bethe-Ansatz equation or something.
Yes, it's actually very similar.
Yeah.
In fact, yes, that's exactly how it does. So you essentially look at what happens when you exchange the momenta.
Uh-huh.
And that's just the term that goes in the Bethe-Ansatz, the thing that factors. But it's more trivial in the Bethe-Ansatz because it's just two particles. Okay. So this is actually in the last paper, which is the last of the two D75 papers. So there's some older work, which is more, some of which is older, some of which is newer, which is more concerned with the string spectrum. In the D74 paper, that picture I drew up there, essentially corrections of this kind, are used to calculate corrections to the horizontal string tension. So in fact, the weakness, I think, of the first paper was not really in properly understanding, well, in just assuming that physical picture would be correct without really calculating the effect of H1 in detail. But that's done in this D74 paper. And you see, in fact, that things like this essentially can be calculated as a kind of vacuum polarization. So if we look at the J0 operator, there's an exact form factor that allows us to consider this vacuum polarization-like loop. This is an FZ particle here, and so is this. And so in that paper, this diagram is calculated. And that allows you to find corrections to the naive horizontal string tension.
Are you using these exact results for the matrix elements?
Yes.
J at each of the vertices?
Yes, so let me write those
Stitch
down.
them together with a propagator.
Exactly. And you also have to time order because these things are designed really for Whiteman functions, not for time ordered products. But so there are things like that. So the exact matrix element is this. So let's see, M1 cosh theta 1 minus cosh theta 2. covariance factor. So all of this, by the way, is what you'd get for just a free field theory, which transformed properly under the global rotations. But then there's this other factor, which is exp to the minus the integral from 0 to infinity over some auxiliary parameter xc. And this thing is essentially just this vertex.
So the vertex doesn't seem to be small in any sense. So why is it that that's the only diagram that you have to think about?
Well, in principle, you could think about more. This is a random, if you like, it's a kind of random phase approximation. And what it's based on is the assumption that this point and this point are close together, so it's a short distance expansion. And the way to do this formally, by the way, is to reintroduce a zero and write this complicated thing as something which is linear in each of the currents times some auxiliary parameter.
So it's not quite clear that you're not just expanding in G0 prime. There are other approximations.
There are other approximations. If we're going to be completely honest, yeah. So there are other things done as well. So I have a little time left. Anyway, if you want to see what the answer is, you find that the horizontal string tension so that's the leading thing, but then there's another factor. Well, maybe I'll just write this numerically. So there's a correction. Okay, so now there was a problem which I was actually trying to solve. I've been trying to solve for a while now, which after a lot of thinking, and maybe it was just that I wasn't thinking about it in the right way, but now is solved. And that's the problem of what happens when we go back to our original problem up here that I mentioned of putting a quark and an anti-quark separated vertically. What are the corrections to the string tension in that case? Sure. Sure.
So M1, you probably want to make some dimensionless ratio with that so that we can understand.
Oh yeah, geez. What did I do there? There's probably an A here, I think, if I do this correctly. And
that's related to the underlying parameters of the model, presumably by some formula like the exponential that you've written down here.
Yes. Yes. And I think, in fact, if I really do it correctly, there's another G0 prime here.
Good.
Okay.
So then it does look more like an expansion of G0 prime.
Right. Right. And it's not perfect. It's really. It's really, see, the thing is that this is the only form factor of the currents that we actually know. So we can't really do better than that.
Sure.
Okay. What about the vertical case? So here, we've got a quark and an anti-quark, and we can join our particles this way. And how do we deal with that problem? So there are corrections to the naive result, which I wrote down, just the gap divided by the lattice spacing. And so it seems desirable to try to work out this problem in detail. So in fact, what we need is not this matrix element, but the crossed matrix element. Essentially, by taking one of these external particles and bringing it around to the other side, we do crossing, and so what happens just is that this pi I disappears. And then what we need to do, what we really need is this quantity. So we take an Fz particle, say at Z1. We consider this thing located at some x1, like this. So that's obtained just by taking this was calculated by Karofsky and Weiss in 1978. This is just the crossed matrix element, but of course we have to get this from momentum space. This is the Fourier transform of 1 over square root of 2e1, 1 over square root of 2e2 of p1, k1. I use the rapidities theta over here, but it's easy to translate to momenta. And so what is this thing? This tells you what the color distribution is. So the reason why this problem is actually kind of subtle is if you try to solve it just naively, the potential between these two guys in the horizontal direction is linear. So if we try to move these things apart, we just get a linear potential. That's a completely stupid looking thing if we try to calculate quantum corrections. But of course the potential isn't really linear at short distances. So if we try to take particles of this kind and put them very, very far apart, call this thing r, the potential is going to look like some p of r. And for r very large, this is proportional to r. But for r small, it won't look like that at all because the color charge of these Fz particles is actually smeared out. And this thing tells you exactly how it's smeared out. So this color smearing actually leads to a quadratic potential at short distances. And so that tells you that if you make a small gradient approximation, saying that the string isn't excited by very much, if you're trying to calculate the ground state, that should be a good approximation, that you can use this quadratic potential, and then you just have a transversely oscillating string.
Somehow you should be able to use the asymptotic freedom of the principal Carl model to tell you about that other region, right?
Well, in fact, what the asymptotic freedom of the model tells you is that at short distances, it tells you about the short distance effects. So in fact, this thing really is a way of if you like, of probing short distances. So without this, you wouldn't be able to know what the potential is at short distances at all.
So why is it r squared?
Why is it r squared? Okay, what happens is that this thing goes like e to the minus a constant times z1. Let's see if I want to write this down correctly. It's yeah, that's right. Okay, it's z1 minus x1 squared times delta z1 minus z2. And then there's some prefactors which depend on the color. So what it tells you is that the current, this J naught, which is just the color charge, is a Gaussian. It's got a width that's smeared out by that constant c. I could write that down for you, but it's probably not very
What's the
illuminating.
scale of this new potential? R squared?
It's of the order of the mass gap. So this c really goes like 1 over the mass gap. In fact, this goes like m1 squared, roughly, with some dimensionless constant.
You should have some coefficient of dimension 3.
Dimension 3. It does have a coefficient, and the dimension is the right dimension, but I think it's not dimension 3. I think it's dimension 1/2. But
You wrote the potential which is proportional to r squared.
yes.
So we should have a coefficient of dimension 3.
Yeah, I mean, if you want to, the dimensions check out. If you want to see in detail what the potential looks like, I can write it down for you. Yes, strictly, well, okay, I'll write down the whole Hamiltonian for you if you like, so we can see it. How am I doing on time? I'm almost done.
Thank you.
So
Yeah, there's plenty of time.
So we find a string Hamiltonian, H string, and this is equal to m over a times, I guess I'll call it L here. We have minus 1 over 2m. So this is a non-relativistic approximation. This is the sum over the x2s between the two quarks. And we have d squared by dz of x2 squared. So this is the one coordinate of the Fz particle. Then there's minus 3 g naught prime squared over 2 g naught to the fourth ma squared times the square root of a over 2 pi. And a is a number that turns out to be 1/12 minus log 2 over pi squared, which is about 0.131. And then here we have a sum on x2 of 1 minus p of z of x2 minus z of x2 minus a. And p of r is equal to 1 plus m squared r squared over 4a for r much, much less than m to the minus 1, and the square root of pi over 2a times m times r for r much, much greater than m to the minus 1. So I think the dimensions all check out if you want to take a look. At least I checked them before, unless I made a mistake. So
P is now dimensionless?
P is dimensionless. And there are also some boundary terms. So terms near the quarks. So, which I didn't write down. So this, of course, is the old string tension that I mentioned before. And these m's are all m1s because this is for SU2. What's that?
For small distances, it more looks like a constant.
No, for small distances it's quadratic. It's just a gradient squared.
It's just the fact that you put a 1
One
in.
minus.
Because C minus C
Yeah.
is like
Right. Okay. So anyway, this is, as I said, this, if you look now in the small gradient approximation, you would ignore this thing, which of course is important because if you try to pull your particles apart, you really do have a linear potential. But at short distances, because of color smearing, we have a quadratic potential. And now what we can do is we can work out what the ground state energy of the system is. So this is gives us a potential, which depends on the separation L, which is m over a minus 2 root 3 over pi g naught prime over g naught squared a squared times L. So here's the leading correction to the string tension. And we also find a second term, which is of order 1 over L, which you'd expect. And then there are terms of order 1 over L squared. So this is the thing that I hope to put on the archive in the next couple of days. Okay. This is everything that I've been able to calculate. At least I've tried to summarize it for you so far. But since I guess I have a little more time, let me tell you where I hope this can go. So this is now a bit more speculative than what I've said so far. So I have a conjecture that you can actually use this stuff to say something about honest-to-God, super-normalizable 2+1 dimensional gauge theories. And that would be interesting because right now all we can do with these theories analytically are strong coupling expansions. There's no analytic weak coupling method that I know of, unless you put in a mass somehow by, say, a Chern-Simons term or something. I would appreciate any criticism on this, but it's a little bit speculative, but the idea is the following. Suppose you want to take this relativistic theory and imagine that it has a non-relativistic limit. So we take ordinary, not anisotropic, but ordinary Lorentz invariant 2+1 dimensional Yang-Mills theory, and now ask, suppose we look at energy scales which are much less than the mass gap of that theory. So we're assuming it has a mass gap. but we're going to think, what happens if we look at scales that are much, much less than that mass gap? In other words, a non-relativistic approximation, which only exists for the quantized theory. It doesn't exist for the classical theory at all, because the theory of gluons, of massless gluons, doesn't have any non-relativistic limit.
Nothing happens at scales much less than the mass gap. That's by definition.
Well, okay, so less than the mass gap, but not so much less that you just have static particles.
Yeah, I'm not sure what that inequality means, but
Okay, so the idea is we're trying to look at particles which are just barely allowed to move, non-relativistic particles. So the idea is to make some kind of a non-relativistic approximation. Now, if you do that, so I'm going to write down the Lagrangian. As I said, this is not really a classical idea at all. So, but if you imagine putting the speed of light into the Lagrangian of ordinary 2+1 dimensional gauge theories, what you get is that it's c times the integral of dt integral d squared x, and we have the usual first term, 1 over 2 e squared times trace of f0 I squared minus c squared over 2 e squared times the trace of fij squared. So f12 squared. So let's define, if we put a cutoff into this theory, so put in cutoff A, and define G naught prime equal to G naught divided by C. So the idea is, in principle, you would want to justify this by something like an anisotropic renormalization group. So if you do real space renormalization groups, actually they have the problem that they make coupling constants different in different directions. The idea is if you did a good anisotropic real space renormalization group, you should wind up with some theory that has a coupling constant much, much bigger in one direction than the other direction. And so the conjecture is if you do this, what you'll get is some kind of non-relativistic limit of the theory. And that's essentially just taking one dimensionless coupling constant and making it much, much less than the other dimensionless coupling constant. So suppose you try to take this stuff and translate it into the language of what I've been talking about so far and ask what would happen. Can everybody see this board, by the way? It's not too far off to the side. So let me try to make a sort of a dictionary. So here's our anisotropic theory. And here's our non-relativistic limit. So one thing you have to remember is that the anisotropic directions are different. The one that we took in the beginning was that the coefficient of f01 was small. Now we actually want to take the inverse coefficient of f12 to be small. But presumably we can make a Euclidean rotation and that will work. So here, I never told you that the space-like Wilson loop has an area law, but it does. If we look at the space-like Wilson loop, in the non-relativistic limit, this should go like e to the minus t times v of r, where v of r is our static potential. I called it L over there. Maybe I should change that. And then what would correspond to the mass gap in the non-relativistic limit? Well, it should be a correlation function of some sort. And it turns out here it would be a time-like correlation function you'd want to consider, but we translate over here, it turns out to be the correlation function in the two direction. So this would correspond to j mu of x1, x2, j nu x1, x2 plus t. And this should go like e to the minus t times the mass gap in this theory times c squared. And so the question is so this is the only thing I haven't really studied yet much in this theory are correlation functions in the x2 direction. And I suspect that this can be calculated, or I'm pretty sure this can be calculated, again using the exact form factor. But I have no idea yet what this would look like. So the conjecture then is that the ratio of the string tension to the mass gap should be something, squared. The question is, does this exist as A goes to 0? And if it does, then we have a prediction for the isotropic theory. So in other words, in the non-relativistic limit, you should still have confinement of sources. You should still have a mass gap in the theory. So I'm really thinking of a non-relativistic limit in which we've integrated out some of the degrees of freedom. And if this thing, the only project I sort of really, there are a lot of little projects which can still be done and all of this stuff. The only big project that I can think of that's left is to calculate this thing and see if this limit is sensible. And if it is, then I think that could be regarded as a decent or a decent prediction for the isotropic theory. If it doesn't exist, then it's a nice model and nothing more. So, thank you.
So I didn't quite understand the last bit. You sort of want to do the same thing, but now singling out the time direction as special rather than one of the spatial directions? You want to have this kind of...
Right.
But in a Euclidean language and have this being the time sequence.
Yeah, right. And so what I guess I'm trying to say is, see, whether or not this works, I'm firmly convinced that this is really a caricature of how confinement should work in 2+1 dimensions, even for the isotropic theory. It somehow, well, I mean, that's my own feeling. I mean, I can give you reasons why I think that that's true. But in any case, I mean, I feel very strongly this is really how it works at weak coupling. And so I'm trying to see if there's some way I can continue this picture over to the isotropic case. This is the only way I can think of right now. Otherwise, I'm just dead wrong, and I need to go on to something else.
So there have been claims in the literature about, I mean, related approaches, perhaps combined with large N.
Yeah.
The work by Rob Lee.
Oh, God.
Would you like to elaborate on
I'm sorry. This is being videotaped. No. Okay. That's the problem with the small group of people. You know, things get too personal. Okay. Look, those guys wrote down a conjecture for the vacuum. It was motivated by strong coupling calculations. It agrees with the resummed strong coupling vacuum that Nair and Carabali wrote down, and also Jeff Greensight in the early 80s wrote down the same thing by doing a lattice resummation for strong or for weak coupling. It doesn't agree in the intermediate coupling region, and
doesn't agree with what? Sorry?
it doesn't agree in the intermediate coupling region with the vacuum. And
Sorry, how do you know what the real vacuum is?
no, with the strong coupling. In other words, it doesn't agree with the other results.
Oh.
But I don't know what the motivation for their vacuum is. So I've tried to understand it. I would say now that I think we shouldn't take it too seriously. It's not a weak coupling approach.
So you characterize it as kind of an ansatz for what the vacuum wave.
It's an ansatz. It's not even really a variational ansatz. Okay. I don't want to knock these guys too much because I think they worked hard. They had some interesting things to say. I'm skeptical that their vacuum is the correct vacuum. So there were some ideas by variational approaches people have tried, but I don't know how good any of that turned out to be in the end. As far as I know, there's really no competitive weak coupling approach. And I should emphasize, of course, so I really should say for the isotropic theory right now, there is no weak coupling approach. And I'm attempting to make one here, but so to be fair, I mean, nobody has solved this problem.
It's not clear why there should be a weak coupling approach, right?
Well, I don't know. I mean, you know, you have a problem, maybe you can't solve it, but there certainly is a weak coupling solution, I think. I mean, the string tension should have some kind of reasonable behavior. I think you can make a pretty strong argument that the string tension should go like the coupling constant to the fourth power, and the mass gap should go like the square of the coupling. By the way, this works out very nicely for strong coupling expansions in 2 dimensions. So, sorry, in 2+1 dimensions. So Nair and Carabali's results and Greensight's results have nice continuum limits. In fact, there were some Chinese guys who sort of discovered this for Greensight's approach. The question is, are the continuum limits the right ones? So naively, the mass gap, because of the form of the Hamiltonian, is guaranteed to have spectrums of the continuum coupling constant squared. And that's just because of this relation that this coupling squared is just that coupling squared times A. And the reason why the string tension in these approaches works out to be of order e to the fourth is because when you look at what the vacuum is, it turns out it goes roughly like the exponential of b squared times something in front which has the right dimension. So b squared has dimension 4. You're integrating over space, which has dimension -2. So what's left over also has to have a dimension 2. It turns out just the right power of the coupling constant to give you a string tension going like e to the fourth. So that's a very special property of 2+1 dimensions. It doesn't mean that the strong coupling expansions are right, but they do give answers which scale in the right way. I think what people would like to argue is that those expansions converge, and that's the question. Everybody has a cutoff when they do these things. Carabali and Nair have a point splitting cutoff, and of course other people had a lattice cutoff.
Again, I mean, I'm not sure whether one would really expect, without taking a large n limit, one would expect to find convergent series for these.
Yeah, I don't know. I don't know.
That's not generically the case.
Yeah. Yeah, it's possible that you need some other expansion parameter. Yeah, it's possible. I don't know. This stuff, you would wonder what the large n limit of these form factors is. I don't know if anybody's thought about that for a model which transforms under the adjoint representation. That's actually an interesting question. We know the S matrix.
I think you could do the calculations that you've been doing here with that in a more precise way in that limit, because you can calculate. I mean,
okay.
If you take the large n limit of the principal Cara model, I'm pretty certain you could calculate the leading order behavior of any
Right.
given correlation function.
Yeah.
Whereas with this approach, you're really limited to special ones, right?
Yes and no. The problem is that you could certainly calculate it perturbatively. The leading form, in fact, would look very much like this, because this is just what you'd have for a free field theory. So the question is, what is this thing? Can you 1 over n expand it somehow? And the problem is you need to have a gap in the theory in order to get that. So the problem is, how do you know the S matrix, but to get the form factor, you need a little more information. So the S matrix trivializes in the large n limit. It just becomes that for a free field theory.
You still have a gap in the large n limit, right?
Yeah, you have a gap, so you could just guess that it's the free field result and see what the 1 over n corrections are. So now we're really talking about integrable field theories. We're not talking about 2+1 dimensions anymore. So I've actually been playing around with the large n theory and seeing if there's some expansion for the form factor. And that would be kind of fun if you could get that, because the form factor, everything should be somehow simpler. Maybe at leading order and n you can really do more.
Should be able to. You've got a kind of valid, effective action, right? The large n.
Yeah, I would hope so. I would hope so. I don't know. It sounds like some people here are real I mean, I know of at least 1 or 2 people here are experts on integrable quantum field theories. So maybe someone here can tell me more. I actually started off doing this stuff without knowing much about this field, and I had to learn about it. So some of you have been doing it a lot longer than I have.
Well, no more questions. Thank you. I guess for people who fancy going over to CMS for lunch, should we meet in the lobby at 12:30?